overview of how homotopy enters in physics. So remember, uses of, this is the overview of the uses of homotopy field theory. And so we were looking at a fairly general situation of theories of scalar fields mapping from some space-time manifold of dimension d to some target space of dimension n. And the first thing we were talking about were instanton sectors. So for example, if S sub d is some compact space, some compact space-time, then we would divide up our space of maps from SD into Mn in components, and then that is the set of homotopy classes in the compact open topology. And then I went through a rather long example where S sub d, space-time was either the interval or S1. And we saw that we had to sum over instanton sectors. There was one unfinished piece of business, which was that I didn't show you how you can evaluate this path integral of e to the minus phi q times some constant minus I over 2h bar t d squared by d tau squared phi q. I gave you a physical argument for that, where phi sub q at 0 equals phi sub q at 1 equals 0, say. Then this is, on general grounds, just a determinant, because it's a Gaussian integral, a determinant of the quadratic form here, where the quadratic form should be thought of as an operator on the space of functions of tau, some boundary conditions. So how do you define these infinite dimensional determinants? This is an infinite dimensional quadratic form. Well, in general, if O has eigenvalues lambda n, suppose it's a Hermitian operator, it has eigenvalues lambda sub n, then we want to make sense of the determinant of O, which is the product of lambda sub n. So the first thing we can say is that it's 0 if 0 is in the spectrum of O. Now, if 0 is not in the spectrum of O, then what we do is we define the zeta function of the operator O, which is by definition lambda sub n to the minus s. And then because the eigenvalues of a nice operator, and this is a nice operator we have here, because the eigenvalues tend to infinity, in fact, you can say how they tend to infinity, but let's not. Then this defines an analytic function of the complex variable s for sufficiently large real part of s, and these are theorems now, has an analytic continuation to s equals 0. So the idea of, I believe it was Ray and Singer, was to define this as the exponential of minus zeta prime at the origin. And that's called a zeta function regularized determinant. Okay? Now, why is that a sensible thing to do? You see, in finite dimensions, minus d by ds at s equals 0 of lambda to the minus s is equal to exponent, whoops, something's wrong. No, nothing's wrong. Is equal to log of s, log of lambda, excuse me. And so you would have a sum of log lambdas in the exponential, and that's the same thing as a product. And so, in particular, in this example here, we would reproduce the quantum determinant, which was just right for those two ways of evaluating the Euclidean propagator to be equal. Now, another example. This was an example of where we sum over these different sectors in the path integral, and it's important. Another example is in string theory. So there we have in a Lagrangian formulation, a Riemann surface, and we have maps phi from a Riemann surface into a space-time, which in some interesting applications would look like R4 for our 4 dimensions of space and time that we observe times K, some compact internal manifold. And so then the field space sectors would be classified by the homotopy classes of sigma into K. So for example, if sigma is just equal to the 2-sphere, that would be pi 2 of K. Now, the action in this case is the kind of nonlinear sigma model action, excuse me, the kind of nonlinear sigma model action we had before, where we use a metric both on the world sheet, as it's called, and on space-time. But in string theory, there's a very interesting extra thing called a B field, which is a locally defined 2-form on the target space. And you're supposed to pull that back with phi and integrate over the Riemann surface. And in many, in some important examples, B is a closed 2-form. And in fact, this integral then only depends on the de Rham cohomology class. On B, the de Rham cohomology class. And on the map phi pullback from H2 of K to H2 of sigma, which is just isomorphic to Z. So if you write the de Rham cohomology class of this B field as a sum of, say, theta I, EI, where EI have integral periods, then you can define a bunch of integers analogous to the degree we talked about last time. So these are integers, integer degrees. And then the different non-trivial sectors are going to be weighted by the exponential of 2 pi I, theta I, di. And then we would have other stuff on the path integral, and then we would be summing over these multi-degrees. And these theta i's can make an important contribution to the path integral. And in fact, you can do an example of this yourself, which is just to consider the case where sigma is the torus mapping into a space-time, which is also a torus of some higher any dimension, in fact, for this exercise. And it's very similar to what I worked out in detail last time with just a circle mapping into a circle. It's a little bit more elaborate. but you can, I think you have all the tools to investigate that. And that's an important calculation in string theory. Now, okay, so that's some examples of where instanton sectors come up. Now, even, I want to stress something, that even if space-time is topologically trivial, say S sub d is r to the d, the action can define a non-trivial topology on field space because we require it, at least if we're doing some kind of semi-classical analysis, we require it to be finite. So finiteness of the action is an important principle. So for example, if we take our S of phi to be, now let's just take a Euclidean space-time, d-dimensional space-time, with a Euclidean signature target space, so then our action is going to look like this: g mu nu of phi, d alpha phi mu, d alpha, taking Euclidean space phi nu, plus u of phi. Then you see I should since I'm integrating over this non-compact space, I should worry about the non-compact integration. And a good way to deal with that is to let x equals r times x hat. So x hat is on the d minus one-dimensional sphere. And so the metric on space-time is just d squared plus r squared. Let's call it, let's say, gij d theta I, or dx hat I, dx hat j. So the round metric on the unit sphere. And so then we can separate this integration here into an integral from 0 to infinity. I'm going to write it this way: dr over r times an integral of over the compact sphere. And then what goes in here is going to be r to the d, g mu nu, dr of phi mu, dr phi nu, plus r to the d minus 2, g mu nu, g over ij, di phi mu, dj phi nu, plus r to the d, u of phi. Okay, so what we have to worry about is the integration at r equals infinity. Okay, so in order for that to be well defined, we want dr of phi to go like 1 over r to the d over 2 plus epsilon as r goes to infinity. And then the other directions, the angular directions, have to go like r to the d minus 2 over 2 plus epsilon. And then finally u of phi of r x hat had better go like 1 over r to the d over 2 plus epsilon, where epsilon is something positive. So then we'll have convergence. And so what this implies is that the limit as r goes to infinity of phi of r x hat has to be some constant independent of angles. Okay? So the field has to go to some constant at infinity independent of angles. And moreover, because of this, you see it has to go, and in fact, so phi naught has to be a 0 of the potential. So if the potential is, if phi isn't going to a 0 of the potential, you're surely going to get an infinity in your action from that term there. Now, because of this, we learn that we can define, that phi defines a map from SD infinity to mn phi naught. Okay? Since we're going to a constant at infinity, we effectively are defining a map from the d-dimensional sphere. Even though we're doing physics on Euclidean d-dimensional space, there's an effective map here, And so the finiteness of the action has imposed some interesting topology, and that means that if we look at, say, maps from one to the other with finite action, that the components of that is going to be pi d of Mn. Okay, so as an example of that, and I won't work that example out in gory detail the way I did before, but a very famous example is the O3 nonlinear sigma model, also known as the CP1 nonlinear sigma model, where you have a map traditionally called N, which goes from R2 to S2, but usually that S2 is thought of as sitting in R3, so you have three fields, N1, N2, and 3 fields of X, with a constraint that Ni and Ni equals 1. And, okay, so then the action is 1 over lambda squared, where we take the, or let's call it lambda subcoupling constant. We have the natural metrics, the round metric here, the Euclidean metric here. So we do that, and then we can add a theta term, as it's called, where we multiply that by the degree of n. You see, in this case, the effective map we get from finite action would give us a map from S2, the one-point compactification of R2, to S2. So, as we saw last time, pi 2 of S2 is z, and that's measured by the degree of this map. And that's what we put here. And in fact, last time I even gave you an explicit formula for the degree. And this is known to have, this theta angle is known to have non-trivial effects on the physics. So, for example, at theta equals 0, the spectrum has a triplet of massive particles. You see, there's an O3 symmetry of the model because we can rotate. There's a global O3 symmetry. We can rotate that target space sphere. And so the spectrum of the Hamiltonian should respect that symmetry, and it does. And so you have a triplet under that symmetry. And it's also known that if you then turn theta to pi, then the spectrum has a doublet. So a representation actually not of O3, but of SU2. You have a doublet of massless particles. At theta equals pi. So you see the spectrum of the theory depends rather strongly on theta. This is an old and famous result of Affleck and Haldane. And Ian Affleck has some nice Lazouche lectures where he discusses that.
Excuse me.
Yeah.
So for other value of theta, you get a smooth transition?
It's a research question. I'm not an expert on this. But I believe it's not known exactly how to solve the model. The model is integrable at these two values. I should have said that these two values are distinguished because this term breaks CP invariance unless theta is 0 or pi. So these are the two distinguished points where CP invariance is preserved. And in fact, the model is integrable there. Now, I don't know, I'm sure Lee Khanov would know off the top of his head, if the model is integrable away from these two values of theta, but I do know that there are recent papers where people are trying to understand how the spectrum interpolates. So it's a good question. It's a good question. So, indeed, what happens to, you could ask what happens to these particles as you tune theta from one to the other.
Is it part of the phase transition?
Yeah, well, indeed, there's a lot of discussion about whether there are first order or second order phase transitions and so on as a function of theta. Okay, so that's all I'm going to say about instanton sectors for now. We'll be talking about gauge theory instantons later on in the course. But now I want to say some words about soliton sectors. So we've discussed instanton sectors. So soliton sectors are very similar, except now we're working in the Hamiltonian picture instead of the Lagrangian picture. So we're splitting our space-time now as explicitly time times some d-1 dimensional space. So this is time and this is space. And now a simple remark is that time evolution is a continuous process. So if we start with a field configuration at some initial time, call it phi, then this phi will evolve continuously under the equations of motion, and that, among other things, defines a homotopy. So time evolution defines a homotopy of this map. At fixed time. So now we're looking, when we classify soliton sectors, so now we expect that what's relevant is the homotopy classes of SD-1 into Mn. Then that decomposes our configuration space into different connected components, and then by the correspondence principle, these components should lead to different sectors of your Hilbert space. Okay, so before, when we were talking about instantons, we were talking about different components of the space of all fields we integrate over in the path integral, and then the path integral would be a sum over these different sectors. Now it's conceptually a little different. The space of field configurations at a fixed time breaks up into components. Those field configurations, are, if they're solving the equations of motion, should, by the correspondence principle, be some kind of semi-classical description of quantum states. And so we now have quantum states in these different components of Hilbert space, sectors of Hilbert space. That's actually a pretty subtle thing to make precise. So, yeah, so I wanted to spend a good bit of time today giving you some examples of that. So the first example, again, is string theory. So in closed string theory, this SD-1 would be S1. And so the components of configuration space is just pi1 of Mn. And these are called winding sectors. So, so string theory has these winding sectors where a closed string winds around some topologically non-trivial loop in the target space. And these are different components in the space of fields. And these can be very important fields and lead to extremely non-trivial effects. For example, in string theory, I want to explain why. Maybe I should have put this in. But one dramatic effect of the existence of winding sectors is the following. I claim that a closed string with a target space, let's say, which is a torus, S1 times S1 times S1, where all of these circles have radii r, is equivalent to one where all of the radii are 1 over r, or better to say, string squared length. There's a string scale called L, and if you keep dimensions correctly, it's L squared over R. Now that sounds completely outlandish. So I'm saying that if you live in a torus where all the sides are length r, like a light year, okay, it's the same as living in a torus where all the sides are of length string scale, which is, you know, what, 10 to the minus 30 centimeters squared divided by a light year. That's really tiny. It sounds like, I mean, you should feel really claustrophobic in such a torus. But in fact, the existence of these winding modes means that in fact the physics is equivalent. But I'm not going to prove that. I'm not going to attempt to prove that statement to you. That's part of something called T-duality. Now, just as in the instanton sectors, even when S of d minus 1 is non-compact, we can still use, now we use finiteness of the energy. Okay, finiteness of the energy implies a non-trivial topology on the maps of Sd minus 1 Mn, where we now put a finite energy condition on that. And so, for example, if our Minkowski space action, so supposing the Minkowski space action looks like dt, integral of d as d minus 1 of 1/2 g mu nu, phi dot nu minus some h alpha beta, d alpha phi, d beta phi, minus u of phi. Okay, then, parentheses go like that, I think. Then the energy will simply be the integral over S of d minus 1 of 1/2 of g upper mu nu of phi times the conjugate momentum, let's call it pi nu, plus 1/2 g mu nu of phi, h upper alpha beta, d alpha phi, d beta phi. So h is a metric on space, and therefore we're assuming it's positive definite, plus u of phi. All of this times the volume form of h. All right, so now we have a sum of 3 positive definite terms. So if you're looking, say, for static solutions, then the momentum by mu is 0. And now the analysis is formally exactly the same as what we did with the finite action. And so we learned that we were interested in homotopy classes of Sd minus 1 into Mn to classify our Soliton sectors. Oh, sorry. That was way too quick. And so if S of d minus 1 is R d minus 1, then we would compactify that exactly as in the finite action case, and we get pi d minus 1 of Mn. Now, there's one exception to that. Unless d is equal to 2, so that space is equal to r. And so what has caught us there is that there's not one point, there's not a connected boundary at infinity. You can't make a single point in infinity. The boundary at infinity, if you like, is 2 disconnected components of minus infinity and plus infinity. So let me start with the d equals 2 case, and then just say a few quick things about the d bigger than 2 case. Because the d equals 2 case is something where you can do a lot of explicit things. two examples of solitons in 1+1 dimensions. So first example in 1+1 dimensions. So let's just take a single real scalar field with this action. Okay, minus u of phi. And let's take a very explicit u of phi. So u of phi will be gm squared over 8 phi squared minus 1 over g squared. So let's take a moment to think about what's the physics here. So this is a Mexican hat type potential. And so the vacua, the classical vacua, are phi equals plus or minus 1 over square root of g and constant. So those are the classical vacua. Okay, now small fluctuations. About that, well, we would write phi equals 1 over the square root of g plus delta phi. And then we would find a particle of mass m with delta phi cubed and delta phi fourth interactions. And similarly, that would be perturbation theory around this vacuum, 1 over the square root of g, and exactly the same thing would happen in perturbation theory around minus 1 over the square root of g. Okay, now in field theory, we have spontaneous symmetry breaking of the Z2 symmetry that takes phi to minus phi. Unlike in quantum mechanics there would be tunneling between these two guys, and there would be a unique ground state. In field theory, there's an infinite volume of space which prevents that tunneling, and so we have to choose a vacuum, and that breaks the Z2 symmetry. Okay. Now, finiteness of the energy, it means that phi, as x goes to minus infinity, has to go to plus or minus 1 over the square root of g, and similarly as it goes to plus infinity. And so there are four possible sectors here. There's the plus, the plus, the plus plus, the minus minus, the plus minus, and the minus plus boundary conditions, where this refers to which vacuum I'm going as I go into as x goes to minus infinity, and the second one is which vacuum I'm going to as x goes to plus infinity. Are you with me? All right, yes, sir.
I'm a little bit, maybe it's trivial, but why is x need to go to infinity to get these constant values in the vacuum?
Because as x goes to infinity, so the energy here, so let's look at the energy. Gave you the general formula up there. It just becomes 1/2 dx phi squared plus u of phi in this particular case. Very easy formula. Now you see, as x goes to infinity, supposing phi is going to some constant which is not a 0 of u. Well, this guy, this is positive, okay? So this is just going to give you an infinite energy. Suppose we took phi to go to 0, say. Suppose phi went to 0 as x goes to infinity. So that would mean that this u, so you see, if phi goes to 0 and x goes to infinity, then this u of phi would go to some constant, which looks to me like m squared over 8g. And then I would be integrating that over the infinite region at infinity, and that would be giving me a positive infinite energy. And this can only make it worse.
Right, I see.
Right. So thank you for the question.
How do you know that the only vacua can be at infinity? For x goes to infinity.
All I'm saying is that as x goes to infinity, finiteness of the energy forces me to take phi to go to one of the zeros of the potential.
But there can in principle be others at x. Phi can be in a vacuum even if x is not at infinity. Or
oh yeah, phi can do anything it wants. Yeah, right. I mean, it's just it can do anything it wants if we want to evaluate the energy of a field configuration. It has a little bit less free will if we're imposing the equations of motion.
Right.
Right. So we'll see what the equations of motion tell us. Now, the equations of motion have to be supplemented by boundary conditions. Okay? So, for example, if I choose the plus-plus boundary conditions, okay, and I try and solve the equations of motion, then we'll find that phi of x equals 1 over the square root of g for all x is the minimum of the energy functional. So for this guy, the energy is 0, and that's clearly going to minimize this energy functional. And in fact, in this case, you see it's at the vacuum for every x. Okay? And similarly for minus minus. So these are the vacua. Okay? But now I want to say, let's think about the other case. How about if we let phi go to plus, one vacuum as x goes to plus infinity, and the other vacuum as x goes to minus infinity. Okay? That's another component of field space, and I claim that it is that's another finite energy space. So suppose we take plus minus, or minus plus. So phi as the limit of x goes to minus infinity of phi of x is equal to minus 1 over the square root of g, and the limit as x goes to plus infinity of phi of x is plus 1 over the square root of g. Now, there's a conserved current here, rather trivial conserved current. This is sometimes called a topological current. So J mu is epsilon mu nu d nu phi. Okay, that's trivially conserved because if I take d mu on that, I have d mu up here. These are symmetric. The derivatives commute, but this epsilon mu nu is anti-symmetric, so it's a conserved current. And so I get a conserved charge, which is obtained by integrating the time component of the current from minus infinity to infinity, but that's just the integral, you see, dx of phi from minus infinity to infinity. So that's phi plus infinity minus phi minus infinity. So you see, if that's 0, then it's conserved. It can't go to the other vacuum, the plus-plus vacuum, where it's not 0. So Q is conserved, what's called a topological charge. Is equal to, I guess it's 2 over the square root of g in the minus plus vacuum and 0 in the plus plus vacuum. And so there's no way that one solution can evolve into the other. And indeed, trying to force your fields to evolve, trying to deform the fields from this kind of boundary condition to this kind of boundary condition would, because of this formula here, require an infinite amount of energy or an infinite amount of action. Okay, now, yeah.
Maybe it's not so interesting, but this whole thing followed from the requirement that energy is finite over the whole space.
Right.
Space-time. So if we consider the case of compactified space-time, this requirement.
No, then it's different.
Yeah, that's different.
That's why I'm separating the cases.
Okay.
Then it's different, as I said. Then we will look at the homotopy classes as in string theory.
Mm.
You see, finiteness of the energy on a compact space
It's trivial.
is trivial for as long as you look at smooth field configurations. Yeah. And if you're not looking at smooth field configurations, then effectively you're making space non-compact because you have to excise you have to remove the places where it's singular, and so now you're introducing boundaries. Now, in this particular case, this is a very pleasant example because you can actually go a lot further. So you can now minimize that energy functional, and you'll find that requires that dx squared phi is u prime of phi, and that's minimizing the energy. So delta E equals 0 for that. And now you can multiply this by dx of phi and then some integration by parts. And so it immediately follows, using the boundary conditions, that you have that, which is first order differential equation. So now you can actually solve for this this minimum of the energy. And so you see now we would solve this by integrating from minus 1 over the square root of g to plus 1 over the square root of g. Okay? And find the actual phi that minimizes the energy in this topologically non-trivial sector. And if you do the integral, you'll find that phi is plus or minus 1 over the square root of g times the hyperbolic tangent of m over 2 x minus x naught. Okay, so let me make a few remarks about this. Yeah, one other thing. Well, I'll come to that in a second. So let me make a few remarks about this, because these are general lessons we can get from this example. So the first remark is that what does this field look like? Well, it looks something like that. So near x naught, it makes a transition from the minus vacuum to the plus vacuum, you see? And it makes that transition rather rapidly on a scale of 1 over m. So most of the time, it's exponentially close to being in one of the two vacua. So it spends most of its time in one of the two vacua, and then it just hops from one to the other. Okay? And you also notice that it has a center, x naught, which is not fixed by anything I've said. So in fact, there isn't a soliton. There's a whole family of solitons. This solution is called a soliton. And there's a whole family of solutions parametrized by this x naught. Now, why did this x naught come up? Well, it came up because of the translation invariance of this equation here. So this equation is invariant under translating x to x plus a constant. And so we should be able to get solutions, new solutions, by translating x by a constant. And so that's why there's the whole family of these things. This is called a collective coordinate, or a moduli. So this is a simple example of a moduli of your soliton. So there's a whole parameter space of solitons. Now, if you calculate the energy density of this, the energy density is m squared over 4g times 1 over cosh of m over 2 x minus x naught to the 4th power. And so this thing is very sharply peaked around x naught. So because of this, it's called a lump sometimes, or a soliton or a lump. Yes, question?
So if x naught is a continuous parameter, is this a particle?
Yes. Yes. So first of all, it looks classically like a particle. It looks classically. You see, in the plus vacua, as you know, we get particles once we go to second quantization. But the amusing thing about solitons is that classically, we don't even have to go to quantum mechanics. Classically, we have a particle-like solution. And then, when we quantize the theory, there is a state that looks like this. But this does look like a state. Now, we have to quantize that collective coordinate. And that, that's quantizing the center of mass, and you'll get plane waves. You see, you can take this particle, you can boost it, and so on. And so there's indeed a wave function for that x naught degree of freedom. So yes, you have to quantize the collective coordinates of solitons. And that gets to be a very interesting story when you have, say, moduli of monopoles, for example, with some very interesting spaces. Yes?
Is it finite, the number of...
Yeah, so it's going to form a representation of the Lorentz group. Okay? So when you quantize this particle, it's going to give you a representation of the 1 plus 1 dimensional Lorentz group, which you know is infinite dimensional. It's a non-compact group. So its unitary reducible representations are infinite dimensional. And part of that quantization comes from this x dot here, this collective coordinate. And I stress that more fancier solitons come with collective coordinates. So, for example, the gauge theory monopoles that I hope I get to talk at least briefly about, they come in very, very elaborate moduli spaces, the moduli spaces of monopoles, which have interesting algebraic geometry associated with them. And the quantization of those is a very interesting story.
So the moduli space in this example is just a real line.
In this particular case, the moduli space is just the real line. Okay. So the moduli space is just the set of x naught, which is the real line. Absolutely correct. Yeah. So the last remark I wanted to make is that if you integrate this energy density, then you get 2/3. You get the total energy, which is 2/3 m over g. And the thing I want to call your attention to is that the g is in the denominator. So this g here, you see the strength of these interactions was small when g was small. So g is like a coupling constant. So this is a non-perturbative state. So you never would see it if you're doing perturbation theory around one of these non-topological vacua. And moreover, when you do quantize this system, there will be corrections, quantum corrections to the classical formula for the energy, which people have calculated. So and in integrable models, people even get exact formulas of all quantum corrections. Say exactly what the energy is. Okay, that was one example. Now I thought it would be fun to go over another example of solitons in 1+1 dimensions. So example 2 of solitons in 1+1 dimensions. But this is a little more challenging. So are there any questions about this basic example I've just given you? Okay. So this is in the context of what are called Landau-Ginzburg models. So what we do here is the target space is just complex number space, c to the n, for some n. And so, okay, so we have fields, so it's just a linear space. We have complex fields. And we have a complex. And S sub d, S sub 2 in this case, is just good old Minkowski space in 1+1 dimensions. And so then the action is minus kij of phi, d mu phi I, d upper mu phi complex conjugate j, minus k upper ij, dw by d phi I, dw bar by d phi bar j, where w of phi is a holomorphic function. A holomorphic map from Cn to C, known as the superpotential. Okay, so that's the model, and Kij is a positive Hermitian matrix. And since it's not the point of what I'm going to be talking about, I'm going to simplify my life and simply put it equal to delta Ij.
Can I think of K as a Kähler potential?
Absolutely. K is indeed the Kähler potential. You can put a Kähler potential in this space. And, but that's not what we're focused on, so I'm going to just take it to be delta Ij. But you're quite right. In the general model, it's a Kähler potential. Now, moreover, I'm going to assume that this W has isolated Morse critical points. So the critical points are the solutions of dw equals 0, and I'm going to assume that they're always such that they're isolated points in phi space, and the determinant of d2w by d phi I, d phi j, at those critical points, which I'll label phi sub a, is not zero. That's what Morse means. So, for example, if n equals 1, w of phi might be an mth order polynomial. And what I'm assuming is that w prime of phi has simple zeros. Okay, so there are n minus 1 critical points. Okay, so now let's work out the energy in this case. So the energy looks like this. Well, I'm going to write it in a funny way. Let zeta be a phase. Okay, any phase. And then I'm going to write the energy as follows. Okay, first of all, the energy is, just straightforwardly, d phi I by dx, absolute value squared, where I sum over I, plus dw by d phi I, absolute value squared, sum over I. Okay? So that's the energy. Is everybody with me? Any questions about that? Because now I'm going to do something a little funny. Okay. Okay, now let zeta be a phase. And now write this as follows. Write this as dx of 1/2 d phi I by dx minus zeta dw bar by d phi I bar, absolute value squared, plus the integral from minus infinity to infinity of dx of 1/2 of zeta of dx phi I bar dw bar by d phi I bar, always summing over zeta to the minus 1 dx, so d phi I by dx dw by d phi I. Okay, let me write this here. It's d phi bar I by dx. Okay. So you see what I did? Somebody tell me what I did. Yeah, so if you extend this out, but the cross terms here are nothing other than these. You see? And why are the non-cross terms the same as this? What about this? Well, you see that's because zeta is a phase. Okay? All there. All right, and now this, however, is a total derivative, right? This is d by dx of the real part of zeta times dw by times nothing of zeta of w of phi of x. You see? That's why this is a good thing. So now this energy then is written as dx times 1/2 of d phi I by dx minus zeta partial w bar by partial phi bar I absolute squared, plus now I can do the integral because it's a total derivative. And now remember the lesson we just learned before. Finiteness of the energy implies that the limit as x goes to plus infinity of phi I of x has to be equal to a zero of the potential. Right? told you that the zeros of the potential are being labeled by these phi sub A. So let's say that this one, as we go to x equals plus infinity, is phi sub B I. And the limit as x goes to minus infinity of phi I of x is equal to phi I sub A. So phi A, phi B are critical points of W. Exactly, the critical points exactly in the sense that I defined it in the previous lecture. But in this case, it's just saying that dW is 0. Because if it's not the 0, then you see it would be onto the tangent space of TC. Okay. Now, as I was just saying, now if we impose these boundary conditions, now we can do this total, this integral of this total derivative, and we get the real part of zeta times W, let's say W at B minus W at A. Where W of B means W at the critical point phi sub B. Okay. Now, this is true for any zeta. So the best zeta to take is good. There's a mistake here. There's a zeta inverse. Yeah. The best zeta to take is the phase of the complex number W of B minus W of A. Okay, because then this becomes the absolute value. And then we can say that the energy is equal to the absolute value of W of B minus W of A if we can solve the Soliton equation, put it here, d by dx of phi I equals dW bar by d phi bar I. So this equation here is the analog of this first order equation that we had in our example before. Now, one of the really charming things about this model is that you can supersymmetrize it.
I'm sorry, where did the phase theta go in this Soliton equation?
Thank you very much. It should be there, and it's important. Yeah. So you see I'm putting this to 0. So when I do that with this nice choice of phase zeta, now zeta is understood to be the phase of this complex number, then I get the absolute value here. And I think you understood that I'm taking the case where B is not equal to A. Of course, if B is equal to A, then we're in those trivial vacuum sectors. Then the phase is not well defined. The minimum of the energy is 0. The soliton just sits there. It's just at phi A for all values of x. That's like the plus plus and the minus minus sectors of the previous example. Okay, so as I was saying, one of the charming things about this example is you can supersymmetrize this. I'm not going to do that, but just as a remark, as a side remark, you can supersymmetrize this model, adding fermions psi I, fermionic partners, phi I, and then this model has what's called 2,2 supersymmetry, and the formula for the energy becomes exact. Because we have actually an exact quantum formula for the energy of the soliton provided the soliton exists. So you see over here in this example, there was no problem. We chose plus minus, minus plus, and we found that a soliton existed. But there's not any guarantee that you can always find a solution of these equations of motion with these boundary conditions. So that's what I want to discuss now. Yeah.
What do you precisely mean by the energy becomes exact? Like it doesn't receive quantum corrections?
That's what I mean. So I was just mentioning before that in this previous example, with a single real scalar field, I evaluated the classical energy. You can too, and you should. It's just doing an integral, 1 over cosh to the 4th. But then when you quantize this system, then you find that there are quantum corrections to that classical value for the energy, 2/3 m over g. And it's an asymptotic series in powers of g, valid as g goes to 0. And so it's, it's not an exact formula for the energy. But in this case, if you supersymmetrize it, what I'm saying is not true if you don't supersymmetrize. If you just take the model literally as I wrote it, which is just a model of scalar fields, what I would be saying is not true. But if you supersymmetrize it, then you can show that the fermions always give canceling contributions to all the quantum corrections, so that the formula for the energy, namely the absolute value of the difference of the critical values of the superpotential, is an exact formula for the energy. It follows from supersymmetry. But you do have to have a soliton around which you're going to quantize. So that's what I want to discuss next. So, you see, it's not obvious that you can actually solve this first-order differential equation with these boundary conditions. That's what I want to investigate. Now, let me say a word about why it's not obvious. So, it's a first-order differential equation. So you could tell me, come on, isn't there a theorem that you can always solve first-order differential equations? There is a theorem. So if you have an ordinary differential equation, it can be nonlinear, then there always exists a unique solution in a small enough interval. But we don't have a small interval here. We have to go from minus infinity to plus infinity. So in fact, indeed, let's ask, what does this differential equation look like as we go out to x equals plus or minus infinity? Well, near each Morse critical point, we can choose, well, we have W equals, let's work near W, near phi A plus di dj of W of phi minus phi of A, I phi minus phi A sub A, J plus order phi minus phi sub A cubed. Okay. Taylor expansion. W is an analytic function. And by a further choice, by further change of variables, we can assume that phi I equals 0 at the critical point, and W is equal to W of A plus, let's say, 1/2 phi I squared plus order phi I cubed. So I equals 1/2. So we can make that change of variables here. near any critical point. Of course, we need to make different changes of variables near different critical points. But that's just Morse theory tells me that I can do this.
So you still have the 7D.
And wait a second, I actually want to choose my variables so that I have this phase zeta here. Next question.
You have the DI DJ.
Sorry?
You have the DI DJW times 5.
No, I'm diagonalizing this.
It was 1. I don't know.
With one, yeah. Because these are complex fields, so I have a lot of freedom here. Yeah, I'm actually a little worried about one point. But, so to be on the safe side, let me assume that, okay, so this is a complex symmetric matrix with non-zero determinant. And so by a linear change of variables, I can turn it into that. Now, I think you can put this into, make this the unit matrix. But that's actually not completely obvious. So if you want, let's make that a further assumption. It's not true if I took an arbitrary complex symmetric matrix, which say had zero, had zero determinant, then they're counterexamples. It's a point that's bothering me. But so let's, if you like, let's just assume. I think this is guaranteed by Morse theory, so I think it's really okay. So I'm going to put the zeta here for convenience. I could, of course, choose my variables by rescaling them by a constant phase to absorb the zeta, but I don't wish to do that. Okay. Now, let's look at our soliton equation in this approximation. So it's very simple. D by dx of phi I is equal to phi bar I. Okay. We're ignoring the higher order corrections. And the solution of that is phi I of x is equal to k upper I e to the plus x plus the square root of minus 1, not to be confused with I. K tilde upper I e to the minus x, where ki and k tilde I are real. So you see that there's an exponentially growing solution and an exponentially decaying solution. And clearly, in these coordinates, phi equals 0 is the critical point. We want to approach the critical point, so we take either one solution or the other as x goes to the boundary. So that means, so there's a nice exponentially, one solution approaches the boundary condition exponentially fast as we go to the boundary, just like that tanh went to 1 or minus 1 exponentially fast. And then the other solution is terrible. It exponentially diverges away from the solution we want. Now that's why it might not be possible to solve this equation, because you see, it's a first order equation. If you choose your boundary conditions such that at, say, x goes to minus infinity, you choose the one which is exponentially approaching phi a, then you're stuck with it. So once you crank that, now you integrate that first order differential equation to x equals plus infinity, and in general you just have a mixture of the growing and the decaying solutions. So you're looking for a very delicate situation where you have the decaying solution at both ends. Okay, so the question is, can you do that? So now we observe a very beautiful thing, which is that let's suppose we had a solution. Suppose we have a solution. Now I'm not worried about boundary conditions for just 1 second. Let's calculate d by dx of w of phi of x. Well, that's dw by d phi times d phi I by dx. But then by the Soliton equation, that's equal to zeta times dw by d phi I squared. Okay, now that means, therefore, we get a straight line in the w plane. So you see, if I take the soliton, phi I of x, and I calculate w of it, and I let x vary, I get a straight line in the w plane with slope equals the argument of zeta. Okay? So the image of the soliton under this, so the soliton is some phi I of x, which lives in Cn, or if you like, it's a map from x into from space x into Cn, phi I. And then we can compose that map with the superpotential back into C, and I'm saying that the image of that is a straight line. So now here's the w plane, and now we have these various critical values. So here's w of A, and here's w of B, critical values of the superpotential w. So the image of a soliton has to be a straight line in the w plane. The image of a soliton satisfying these boundary conditions, so it's for x equals minus infinity, if I go down here, that's x goes to minus infinity, the image goes down here. Now as I evolve up to x goes to plus infinity, I evolve up to here. So now you can try and classify your solitons. All solitons, potential solitons, have to be straight lines between these critical points, critical values in the w plane. Okay, so now let's focus on one straight line from w of A to w of B. Okay, let's let little w of lambda be w of A plus lambda w of B minus w of A. Okay. So that's the line segment, 0 less than or equal to lambda less than or equal to 1. That's a line segment in the w plane right here. Now, if lambda is near 0, then we're down in this region here. So that means x is going to minus infinity, and phi is going near phi A. And so now we can use our approximation up here. Because if phi is near phi A, then we've solved for this. We've solved the Soliton equation. And so what does it say? That w of phi I is this w of lambda. Well, it says that zeta. Okay, so I'm taking the x goes to minus infinity. So that means I have to kill this growing solution, keeping that one. I have ki e to the 2x equals, sorry, I'm using this formula for w here. So I substitute this solution, the k solution, into the formula for w. So I have w of A plus zeta times over 1/2 of ki e to the 2x. That's substituting this soliton for this approximate formula for w. And then that's equal to w of lambda, that's w of A plus lambda times zeta times the absolute value of w of B minus w of A. Because remember, zeta was the phase of w of B minus w of A. Okay, so this cancels. So I find that ki is equal to, the zeta cancels, is 2 lambda e to the minus 2x times the absolute value of w of a minus w. Okay, so now let's choose some reference x and ask what possible solutions we could have. Well, our solutions are determined by a sphere of dimension n minus 1. And moreover, as lambda goes to 0, that sphere collapses down to 0. Because k is real, remember. Okay, now, that sphere is living in the inverse image of w of lambda. In other words, for any point w in the w plane, we can define the set of phi's such that w of phi is little w. This is an affine variety. Now this is sitting inside Cn, and it's of complex dimension. N minus 1, which is real dimension 2n minus 2. Okay, so when I look at this point here, w of lambda, I know that my solution has to live in this variety, x of w. And I'm telling you more. It's a particular sphere determined by these k's. So inside this variety. So the soliton must live in a sphere of dimension, real dimension, n minus 2 at fixed x. The soliton must live in a sphere of real dimension, n minus 1, that's what we found, inside x of w of lambda. Okay, so we have this complex manifold, x of w, for every w. And what we're saying is that these solitons have wave fronts. You should think of these as wave fronts. In phi space, it sort of looks like this. We have possible spheres, okay, along which this is the solution of ki equals whatever. Okay, there are these wave fronts that emerge from this critical point, phi a. And that is an n minus 1 dimensional sphere inside this complex n minus 1 dimensional variety. Now that variety, so over this w plane, we have some complicated xw of dimension n minus 1. And this sphere is some kind of half-dimensional sphere inside. So you can imagine that this xw is like a Riemann surface, and then the sphere is a circle. Okay? And now as this w goes to one of these critical values, w of a, this xw is becoming singular. So some cycle is pinching. this sphere here is shrinking. So remember, I told you that the sphere is shrinking as lambda goes to 0. Okay, so the wavefront is kind of looking like that. So the solitons must live in a cycle, let's call it delta A of W for every W. Now exactly the same story exists over here. Okay? There's also a sphere in the same XW, also true in delta B of W. So maybe delta B of W looks like this. We can get a solution if delta A intersects delta B of W. So if these, so I have canonically over here a certain complex variety. The solitons have to live in this half-dimensional space, this real n-1 dimensional space inside it. Those are the ones that come from here. Similarly, they're the ones that come from here. And now I have to be able to join them. I have to have a single soliton that goes all the way. So therefore, if I compare the cycle from here and the cycle from here, they better intersect if I'm going to have a real soliton that lives all the way. That exponentially approaches the critical point here, it exponentially approaches the critical point here. Now, it didn't have to intersect. It could have been that the picture was like this, and they didn't intersect. Then you don't have any solutions. Then there are no solitons. So you have this beautiful way of saying this beautiful geometrical way of saying how many solitons do you actually have in terms of this intersection theory. You see, this is a real n-1 dimensional manifold. This is a real n-1 dimensional manifold. And they're sitting inside a complex n-1 dimensional manifold, which is real n-2. So if you think about it, two half-dimensional manifolds will typically intersect in points. Right? So two one-dimensional manifolds and a two-dimensional manifold intersect in points. Right? Here's two one-dimensional manifolds intersecting in a two-dimensional manifold in a point. Two two-dimensional manifolds and a four-dimensional manifold intersect in points. Okay, so these things intersect in points. And so we get a soliton for each of those intersections. Yeah.
Can this in some way be related to twistor space, or is there
To what?
twistors, or is this something completely?
No, this is the beginning of something called singularity theory, which is a really very, very beautiful subject, where you study these complex manifolds and how they degenerate. You see this picture here of this collapsing sphere. Let me draw it again. So you have some kind of control space, this W space, and now you have some complex manifold, let's call it X of W for every W, and then maybe there's a critical point where it collapses to a singular manifold like that. So away from the critical value, the inverse image is always non-singular, smooth. But then you go to the critical value, this is the critical value, and this XW becomes singular. And how does it become singular? Well, there's some sphere in this particular picture. It's a one-dimensional sphere, which has shrunk down to a point. And what I'm saying is that's the general picture here. You have these spheres that are shrinking down to points at each of these critical points. So this is not twistors, but this is singularity theory. And now maybe I people look pretty puzzled. So I'm not sure I will continue this later on in the course unless there's interest. But this is the beginning of a very beautiful story. And if you want more details, you can look at the paper of Cicciotti and Vaffa, Sergio Cicciotti and Kumlin Vaffa. It's on the archive, 9211097. I should say it's related to the currently fashionable topic of wall crossing, for example. Okay. Well, oh my God. That was just supposed to be a little digression. Yeah.
So later we have to glue the Ki and K2 I.
Well, those are just local. Yeah. So those are just, these are only locally valid near each of the two critical points. They're even in different coordinates at the different critical points, right? Because I had to make some change of variables to bring W to this form. So this is true in coordinates where the critical point is at the coordinate values phi equals 0 with this covariant form. So these are even different coordinate systems. So you can't really compare the KIs. What you do know is geometrically,
You look at the lift of that path in the...
yeah, you look at the lift of that path, and what it's saying is the lift of that path always lives in this vanishing cycle. Okay? And so that's what you know by continuity. Continues to be true all the way along this line segment. All the way along this line segment.
And if the
And so you have a vanishing cycle from here, and a vanishing cycle from here, and if they intersect, then you have your soliton.
and then it's unique, or that depends on
No, it's not unique. So you can have many different intersections.
if I think of I lift the whole path, whole this line segment, I will get different Lagrangian cycles.
There can be more than one soliton. So there can be no solitons. It might be that these cycles never intersect. It could be that there are 102 solitons because these cycles intersect in 102 different places.
That means you have 102.
That means you have 102 solitons. Yes. Pardon?
You have 102 lifts of this segment.
That is correct. You have 102 solutions of this first order equation, which is erased, with those boundary conditions. That is correct. I know it's late, but I want to at least mention very briefly. So that was the story in 1 + 1 dimensions. Let me say something very, very briefly about the Soliton sectors in higher dimensions. Okay, supposing we now take space to be R, or space-time, to be R1, D minus 1 with D bigger than 1, D bigger than 2. Okay, so now now space is RD minus 1, and the boundary of space at infinity is SD minus 2, and for D bigger than 2, this is connected. So this was really a special feature of 1 + 1 dimensions, that the boundary at infinity was disconnected. Now it's connected. And now the finiteness of the energy is exactly the same kind of analysis as we did for the instanton sectors. So now the configuration space has components which we can identify with pi d minus 1 of our target space. And let me just mention one very important example of that, which are things called Scurvions. Scurvions. So in that case, we have 3 + 1 dimensions, and in nuclear and particle physics, it turns out to be interesting to consider the case Mn, which is SU2 times SU2 divided by diagonal SU2, or SU3 times SU3 divided by diagonal SU3. these are isomorphic as manifolds to the SU2 manifold, the SU3 manifold, and we can generalize to the SUN manifold. And these are these kinds of nonlinear sigma models come up in describing the low energy dynamics of mesons in QCD. So this would apply to the case where you have two light quarks, like the up and down quark, or if you're willing to tolerate a little less accuracy, you can include the strange quarks, so you have three flavors. So this is what happens when you include three quarks, and then in large N QCD you can generalize to SUN. Well, okay, so now what do we see? Now the configuration space in this sigma model would be characterized by pi 3 of SUN. And what we're going to be discussing later in some detail is that pi 3 of SUN is Z for n greater than or equal to 3. And, 2. And so there are possibly topologically non-trivial sectors where the nonlinear sigma model field wraps all of R3, our spatial R3, wraps it around this, these non-trivial cycles in the special unitary group. And those do support soliton configurations, and those are called skyrmions. And it turns out, rather surprisingly, that if you add a kind of topological term called the Vessamino term, then in fact they are baryons. They act like they are fermions, they act like baryons. So, okay. So, that's enough for today. Let's see, next, it's already Wednesday. So next week we will talk about bundles.